course Advanced Reaction Engineering. So, we will discuss about non-isothermal reactor design with heat exchange. So, that we already have discussed in your previous class. So, temperature profiles and for the reactor inside of the reactors, at the same time when heat exchange is there. So, then the heat transfer fluid temperature also, how that would vary along the length or down of the reactor. So, that we will discuss a few cases. So, already we have discussed that reactions either may be exothermic or endothermic reactions, and that is particularly for the reactions. If we are taking these reactions, it may be exothermic or endothermic reactions. So, depending upon the nature of the reactions, it may either heat evolution should be there during the reactions inside of the reactors, or maybe heat would be absorbed during reactions. So, temperature of the reacting mixtures may fall during the reactions when conversions is increasing or progress of the reactions. So, here one steady state tubular reactor with heat exchange example is given. So, here in these systems you can see this is a tubular reactor or plug flow type of reactor. So, here's reactant is feeding here and that product that is coming out from here. So, that feed inlet temperatures and molar flow rate is this T0, that is the inlet feed or feed temperatures, and that is the molar flow rate, that component A basis, that is written Fa naught, and this is Fa at the exit of the reactor, that way after reactions it is coming. So, here the reacting fluid or coolant or heat transfer fluid that we are passing through this reactor outside as a jacket, through that we can flow the heat transfer fluid either co-currently or maybe counter current directions, means with the this directions reactant mixture is flowing from left to right, and here it is showing counter currents. So, it may be same directions or maybe opposite directions in that both the cases. So, here if we consider let us say exothermic reactions, then if you maintain co-current of heat transfer fluid flow, then so what would be the temperature profile for the reacting mixtures as well as coolant temperatures. If exothermic reactions and flow is counter current, then what would be the nature of temperature profiles of that both reactant temperatures or reaction mixture temperature, at the same time the heat transfer fluid that is passing. So, the temperature profile we can evaluate or we can find or we can see. Okay. So, and similarly for endothermic reactions also, in both the cases we can find out, means what would be the nature. At the same time if the system is let us say adiabatic, means system is the adiabatic, there is no heat transfer or heat exchanger is available or heat exchange possibility is not there. In that case also what would be the temperature profile, that first we will see, and then co-current, counter current and exothermic reactions, endothermic reactions, that we will discuss. So, the nature of different cases we will discuss. So, basically conversions as a function of volume, means along the reactor volume changes, what would be the conversions, and temperature of the reacting mixtures, at the same times Ta volume of the reactors if it changes. So, then this is the reacting T is the reaction mixture temperatures, okay, mixture temperatures, and Ta that is the heat transfer fluid temperatures, and X is the conversions whether the reactions may be exothermic, endothermic. So, these are the things we will discuss or we will see, means the nature of the temperature profiles, conversions profile. So, for that, so let us say first we will consider a reaction A is going to B plus C, that is the product. So, here the reactions is endothermic reactions. For example, first we will discuss about endothermic reactions that we can conduct inside of a reactors. That is the case 1, that is the adiabatic operations we can do. There is no heat exchange with the surroundings, means inside of the reactors it is insulated from the outside. So, when reactions, these reactions will conduct inside of the reactors, there is no heat in or heat out from the system. So, that is adiabatic systems. Under that conditions what would be the temperature profile, that we will see. And this is the another case, as I say, for reaction is endothermic reactions, but heat exchange with constant heating medium. that is the heat transfer fluid that is passing outside of the reactors. Here this is the case 1, so you can see this is the reactors, and here the reactions we can conduct here inside of the reactor, and outside that is insulated, means barrier is there. So, when reactions is take place, there is no heat exchange in between that. So, under that conditions, when reactions is progress, so then what would happen means temperature inside of the reacting mixture. So, that we will discuss. And second case, that is I said Ta equals to constant. So, this is reactors or reactions will take place in these particular positions here. A plus B going to C, A is going to C plus A is going to B plus C. This is the reactions that will take place here, and if the endothermic reactions, then temperature will fall. So, at this temperature means once conversion is progress, then temperature of the reacting mixtures gradually will down or decrease. Means if we initially started with T0 temperatures, so once reaction is progress, here the temperature would be lower than this. Okay. So, this inlet temperature would be higher, but reaction temperature may be different, or maybe this is not this. So, reactor temperatures would be different. Okay. So, here the constant heating medium that we are maintaining in the outer surface of the reactor. So, here this is the outer surface of the reactor. At this particular locations we are maintaining isothermal temperature, means constant heat supply. Means if you point here temperature measures here everywhere. So, everywhere the same amount, the Ta would be the same everywhere. Ta would be, so along the length of the reactor. So, if we measure this point, this point, this point, anywhere the temperature would be the same. So, means constant amount of the heat would be supplied, means outside of the surface of the reactors. To outside of the reactor would be maintained isothermals. Then, so what would be the behavior inside of the reactor temperatures or reacting fluids temperature under that conditions we will see. Next is the case 3, that is the heat exchange with variable heating medium. The variable heating medium temperature, that is the Ta would be variable, means when co-current and counter current flow is there, then at different locations if you measure the temperature, it would be different, since along the length of the reactors reactions is progress, conversion is gradually increasing, then depending upon the reactions, either it is exothermic or endothermic reactions, the temperature along the length will vary. So, at the same time the heating medium or heating fluids that would be passed in the outside of the reactor, its temperature also along the length it would be different. So, it would change. So, what would happen? So, that we will see, and another ones, that is case 4, when T is variable, but the flow is counter current. Here co-current you can see the flow, and here it is counter current. This is the coolant flow and this is the reacting mixture flow. So, opposite directions. In these 4 cases we will find the conversions and temperature profiles along the down of the reactor, that we will see. So, that is for endothermic reactions. Similarly, for exothermic reactions also, if the reactions is exothermic, similarly also if we conduct the reactions in adiabatic operations, so then this, and if it is operate at constant temperature, means coolant temperature is constant. So, outside of the surface of the reactor, so then temperature profile. Similarly, case 3, that is counter current, and case 4, that is the co-current nature of the coolant. If we circulate outside of the reactor and the temperature we are maintaining when reactions is in progress. Okay. So, both the cases means either exothermic or endothermic reactions, 4 cases. So, that way we can discuss. Okay. So, now first we will discuss about the case 1, that is the adiabatic operations and no exchange with the surroundings, no heat exchange with the surroundings. So, under these conditions, so if we conduct the reactions, this is the endothermic reactions, first we will discuss. So, once we conduct the endothermic reactions, so what is the procedure to find the temperature profile or conversion profiles along the length of the reactor. So, that we have discussed in your previous class also. So, this is the step 1, that is the material balance equation or the design equations for the plug flow type of reactor. So, this is the equation 1, material balance equations. Then we have to find out the rate. So, rate law and stoichiometry is there. So, minus R equals to K into Ca, Ca equals to as a function of temperature and conversions, that way you can write, and the fractional volume changes when reactions is there. So, then we can write E equals to mole fractions into delta, that is the changes of the moles from product to reactants, reactant to product formations, and this is the concentrations of the reactants, that initial concentration of the reactant A basis we can find out if you know the partial pressure of the component A, gas constant and temperature. So, then we can find out. So, here if pure component A is present, so then mole fractions pure 100% A we are feeding in the reactor. So, there is no inert or other component. So, mole fractions we can take for pure component of A as a feed. So, then mole fractions we can consider as 1, and then the total pressure and partial pressure would be of course 1 for that cases. And here next step is the energy balance equation. So, this is the material balance equation, this is the energy balance equation. So, the energy balance equation, the progress of the reactions, the temperature along the length or volume of the reactors, this type of equations we have derived. So, whence the systems is the adiabatic operations. So, there is Q part equals to 0. Okay. So, in these equations you can see, so when adiabatic operation Q equal to 0, so there are no means additions or removal of heat in the system. So, then Q equals to 0 means Q equals to this U A delta T. So, if Q equals to 0, then this part we can eliminate, or this part would be 0. So, these equations we can write as this. Okay. So, right hand term in that equation 2 we are eliminating, since the reactions we are operating in that reactor in adiabatic mode. So, then that part we are eliminating, then the equations would be become like this. And in the heat of reactions, this how to find out. So, it is already we have discussed heat of reactions at the standard temperatures, that is the reference temperature, and heat capacity difference if you know at that temperature reactions is occurring we know, and reference temperature, then delta H Rx we can find out. Similarly, heat capacity changes also product to reactants we can find out. This is the general definitions of heat capacity changes delta Cp to find out. For a here's product is B plus C, and these equations would be little bit different, means it was written based on A plus B going to C plus D, but here the reaction is different. So, for that accordingly delta Cp would be product minus reactant heat capacity. Okay. So, here this would be the heat capacity. So, here let us say the reference temperature is 298, reactor volume is let us say 5 dmq, and feed inlet temperature, that is component A feeding at these temperatures, molar flow rates of component A on that is given, let us say partial pressure is given, R that is the gas constants known, and reaction rate constant, that is as a function of temperature, that way we can write. So, if we know feed temperatures, that is given T0, let us say T0 is 1035, we can put it here. This temperature we can vary, means feed temperature to the high temperature or lower temperature. So, then K value will accordingly will change. So, then these are the components we can put in the red equations, and by that we can solve. So, these two equations if we solve, means by ordinary differential equation solver. So, then the nature of that profiles would be like this. Okay. So, here the reactions was, this reaction is the endothermic reactions I said. So, here x axis we are putting the volume, that is changes volume, and y axis that is the if we consider that is the conversions, let us say. So, the conversions will vary, means along the changes of the volumes these directions. So, conversion gradually will increase, this is a PFR reactor. So, it would gradually increase like that, and the reactions is endothermic adiabatic operations. So, then inside of the reacting mixture temperature, here initially we have started with that, and this is the maybe exit temperature or outside temperature. So, we have started with this temperature, since the reaction is endothermic reaction, therefore, with the progress of the reaction the temperature gradually will fall. So, this is the reacting mixture. So, at this particular locations, so this way temperature will fall. So, at this particular location it would be temperature this, and corresponding conversion is this. At this particular reactor locations the temperature and conversion should be this, at this particular locations inside of the reactor. So, here the temperature would be this and corresponding conversion is this, like this here also at this particular location conversion and temperature would be like this. This way it would changes inside of the reactors when the reactions is adiabatic operation and endothermic reaction. Similarly, for rate of the reactions also, if we plot y axis rate, so it would fall like this, means with progress of the reactions conversions will increase, then rate of the reactions gradually will decrease. Okay. So, this way it would be the nature under case 1. Similarly, for case 2 also we can discuss when T equals to constants. So, see here the outside temperature everywhere is the constant temperature, there is no temperature gradient along these positions. So, under this condition only reacting mixture temperature will changes, means from left hand side to the right hand side, but the reacting fluids or heat transfer fluid that we are passing outside of the reactors. So, here means some coil is there, circular coil is there outside of the reactor. So, it maintain isothermal temperatures. Okay. So, similarly also we will do the material balance, energy balance for these reactors. So, here similarly these are the two equations we have, equation 1 and equation 2. So, these two equations we have to solve, and addition to that here T is the constant, means temperature gradient. So, this another step 3, that is the third component, since earlier one was the adiabatic. So, there is no heat transfer fluid that is circulating outside of the reactor, therefore, we have not considered that, but here heat transfer fluid is there and its temperature is constant. So, dT A by dV means Ta is the heat transfer fluid temperature. Okay. So, then that part equals to constant. So, constant if we differentiate with something, so then that would be of course 0. So, then there is no temperature gradient at this along this directions. Okay. So, this part for co-current or counter current, that way we can express. So, the temperature profile or temperature gradient along the volume. So, these particular reactions, when the reactions is isothermal temperature or T equal to constant, in this case see if we plot y axis as x conversions, x axis volume. So, then reactions conversions that would be progress like this, and the temperature of the reacting fluids, that was the constant. So, therefore, Ta this part C it is constant, left hand side here V equals to 0 to V equals to V. So, there is the temperature that we are maintaining T equals to constant, this is horizontal, this is parallel to the x axis. So, there is no changes of the temperature, that temperatures. So, inside of the reactor reacting fluid is there, so reacting mixtures, its temperatures initially was high, and since the reactions is endothermic, so then reaction temperature will fall like this, it would be go minimum at these conditions, and then again the temperature will rise, since after that the conversions not too much increasing. So, but heat transfers that is this fluid temperature is constant, but constant amount of heat that is supplying to the heating medium, but that amount of the energy that is supplying to the heating medium, that is greater than the amount of energy that is receiving by the reacting mediums. Therefore, that would be the less. So, therefore, temperature of the reacting mixtures will gradually increase. So, after a certain locations. Okay. Here you can see, so the temperature, so since the reactions is endothermic reactions, the temperature drop will increase, the temperature drop is there with increasing progress of the reactions, and rate is also decreasing. Here rates also you can see rate this way it is decreasing, and temperature is also decreasing this way, and then it is increasing. So, after a while the supply of energy at a rate greater than the reaction draws the energy. Since endothermic reactions, the reactions mixtures will draw or receives energy from that heat transfer fluids, but that would be receiving amount of the energy is the amount of energy is required for the maintain the temperature, that would be comparatively would be low than that. Okay. So, here as a result means the temperatures of the systems will increase after a certain period of or after a different positions or locations of the reactors. So, it was for adiabatic systems, and this is for isothermals, T equals to constant. So, these are the basic difference you can see here. In case of the adiabatic operations, the reacting mixture fluid temperature that was decreased gradually with progress of the reactions. Here also it is decreasing with progress of the reactions, but in case of the isothermal operation T is constant. So, from here it is increasing. Okay. So, these are the basic difference in between these two. Okay. So, next third cases is this heat exchange with variable heating medium. T is the variables. So, here the systems is either co-current or counter current. Here when T is variables, when T is variables means temperature of the reacting fluid mixtures, that would be variables only when that fluid that is passing outside of the reactor, that is the coolant or heating medium, that may be co-current or counter current. Here we are considering co-current means same directions reacting medium and heat transfer fluids that flowing in the same directions. So, then the material balance, energy balance equations both are similarly we can write, means the reactions we are considering the endothermic reactions, and this is the same reactions we are conducting under these conditions when T is variables. This way heating medium is flowing. Okay. So, reacting mixture is also flowing these directions, and heating fluid medium also outside of the reactors, that also flowing these directions. So, then this temperature profile is also we will have to consider. So, if we in case of the co-currents, that fluid temperature initially it was T A naught and finally it would be T A, means heat transfer fluid temperatures. And if we consider that let us say at a particular mass rate that heat transfer fluid is flowing 0.11 mole per second or kg per second, and heat capacity of the fluid that is passing in the as a heat transfer medium. So, then it has also capacity. So, that you can put it here, heat transfer coefficient we know, and the area per unit volume of the reactors if we know. So, then here it is given, let us say. So, it is also given, means UA given, TA is also given, that is the coolant temperatures. So, then T would vary along the reactors. So, then accordingly the heat transfer fluid temperature also will vary. So, other components means known parameters are given. So, you can see it here for this particular reactions, these are the known components, these are the known parameters. So, we have to put to solve equation 1, equation 2 and equation 3. These 3 equations simultaneously we have to solve by using ordinary differential equation solver. So, then we will get this profile. Okay. So, here temperature of the heating medium is variable. So, here you can see x axis is the volume and y axis is the let us say conversion is progressing like this, and heating heat transfer fluid temperature let us say was started with here, with progress of the reactions it would be vary like this, means along the reactors, since the reactions is endothermic reactions and its outside cooling temperature or coolant temperature will fall like this. And heat transfer medium temperature also we have started with the reactions at T naughts, that is the feed temperature, and then inside of the reactors endothermic reactions, with the progress of the reaction the temperature will fall. So, with progress of the reaction, so it would be vary like this. So, heat transfer fluid temperature and reacting mixture temperatures almost similarly, that is decreasing similar way along the progress of the reactions, and the rate of the reactions is also similarly this way, it also falling or decreasing along the length of the reactors. Okay. So, you can see it more clearly here. So, how this temperature and this temperature, these are the two temperatures. So, here is the reactant temperature or reacting medium temperature, and T A naught, that is the heat transfer fluid temperature progressively decreasing. So, if it is counter current, earlier one was the co-current, here T A is the variables, but the flow is counter currents. So, this way reacting mixture and this way fluid heat transfer fluid medium is changing or flowing. So, here also temperature heating medium or the heat transfer fluid temperature, that is also changing along the volume of the reactor. So, similarly also material balance equation, energy balance equation and heat transfer fluids, the temperature profiles means equation, differential equations is this. These 3 equations you have to solve. So, by putting all known parameters, here only the directions is different. So, then if it is counter current, so in this case the temperature would be profile is like this. See here inside of the reacting mixture temperature would fall, then it is increase. Similarly, the heat transfer fluid temperature will fall like this, decrease and then increase. So, this way it will vary. So, in earlier ones the temperatures profiles for reacting medium and coolant temperature falling down, then it is not increasing, but when counter current is there. So, in that case after a certain positions or location of the reactor, so then again it gradually increase both the temperatures. Okay. So, endothermic reactions, and in that cases, so how 4 different cases we have discussed for endothermic reactions. Now, reactions is exothermics. Endothermic reactions, these are the endothermics reactions we have considered, and in that case what 4 different cases we have discussed, and when reactions is exothermic, similarly also 4 cases would be there. So, adiabatic operations and constant heating medium and counter current coolant flow, co-current coolant flow. In under these 4 conditions also, similarly for exothermic reactions also we can find out the conversion profiles and the temperature profiles for the heating medium as well as the reacting fluid temperatures, how that would vary along the length or the progress of the reactor. So, that we can find out. So, here 4 different cases it has been discussed. So, that is the case 1. So, that is the when reactions is exothermic and operations is adiabatic operations. So, in that case temperatures would variable means reacting fluid temperature, since the reactions is exothermic, with the progress of the reactions conversions will increase like this. The temperature of the heating medium means reacting medium or reaction mixture temperature also gradually increase along the volume of the reactors. Next is the constant, when case 2, that is the constant temperatures, means outside fluid temperature that we are maintaining constant, but the reactions is exothermic reactions. Under that condition, so what would happen? See here, this is the reacting fluid temperatures, that is the initially we have started with T A naught, in that here this is a T A naught, and at different locations also that is the same temperature. See here volumes V equals to 0, here V equals to V. So, V equals to 0 at that particular locations means one end of the reactor the temperature, and other end of the or any part locations of the reactor the temperature remain constant. So, but heat transfer reacting medium or reaction mixtures temperatures, it will gradually increase, since the reactions is exothermics with progress of the conversions is varying like this way. Okay. This is inside of the reactor for exothermic reactions. Conversions will progress like this way. When conversion is increasing, then reacting mixture temperature gradually increase, rise to the high, and then it would drop like this temperature profile inside of the reacting mixture. And when reaction temperature is variable and reacting fluid temperature is heat exchange fluid temperature that is flowing in the counter current mode, in that case conversions is progressing like this. Okay. Inside of the reactors, but the flow is counter current. So, then in this case the counter current and temperature T is variable. Initially you have started with this temperature, reacting fluid temperature. So, inside of the reactors the temperatures of this fluid gradually increase and then decrease. Reacting mixture temperature also gradually will increase and then decrease like this way. T will vary like this and T will vary like this. So, since it is counter current, here T is also variables. Exothermic reactions, in this case this is the case 3 and this is the case 4. So, in case 4 and case 3 and 4 both are the similar, but the external fluid, that is the heat transfer fluid, that temperatures earlier one was the counter current, here we are just co-current heat exchange medium that flows with the reacting mixture. So, under these conditions, see here the conversions will increase like this way with the progress of the reactions, then heat transfer fluid temperature will gradually increase like this, and parallelly heat transfer fluid medium temperature also will progress like this, gradually increase, since the reactions is exothermic reactions and it is the co-current. So, therefore, the nature of both the temperatures would be like this, and so when it is counter current it would be like this, means a particular position it is gradually increased, when then again it is falling, both the temperature falling, and here co-current it is both are rising. Okay. And here in case of the constant temperature it will rise and then fall, and when it is the adiabatic it gradually progress. Okay. So, it is like similar like adiabatic operation and this operation almost similar, but here Ta is not there, means heat transfer fluid temperature is not there. So, in adiabatic operations. So, these are the things. So, means we have discussed. So, in endothermic reactions you can see. So, it was the exothermic reactions, this one means when constant temperature, coolant temperature was constant and the reactions was exothermic, then temperature will rise, then fall. Heat transfer fluid temperatures and heat transfer medium temperatures is constant. Here also heat transfer medium temperatures along the length of the reactor, that is also constant Ta, but the reacting mixtures inside of the reactor, reactions mixtures are there. Since the reactions is endothermic, it is falling and then rising, okay, with the progress of the conversions, and here it is rising and then dropping, and here first dropping and then increasing. This way endothermic reaction temperature profile and exothermic temperature profile, these are the two also you can compare. So, or this way it is actually happened. Okay. So, now it is clear. So, means what is the temperature profiles for different systems, means whenever we are going to design any reactors when with their heat exchange or medium is there. So, then step 1, step 2 and step 3, these are the 3 equations you have to solve, and based on that what are the data will come: volume of the reactor, temperature of the reacting medium, Ta and conversion. These are the data points we have to find out, and then we have to once ordinary differential equation solvers will solve, then by putting all known parameters these tables will come, and if we plot, then the nature of the curves would be like this. Okay. So, conversions versus volumes, heat transfer fluid temperature against volumes, reacting medium or reactions mixtures temperature against volumes we can plot, and we can compare with the equilibrium conversions also. This is the equilibrium conversion, X is the equilibrium conversions for reversible reactions. So, this way we can compare or we can say how close the conversions which we are able to reach for this particular operations. So, these are the things I think it is clear for you, means two different reactions, exothermics, endothermic reactions, and when there is a heat exchange or heat transfer fluid is there. So, then the temperature profiles for reacting mixture as well as the coolant or heat transfer fluid medium temperatures we have discussed, and it is clear. Thank you. So, today is up to this.